So maybe while I'm rubbing this out, we can say a few words about what's going to happen in this lecture. So I will continue on from yesterday's discussion about particular solutions to the wave equation, where we saw yesterday in homogeneous medium that waves propagate for all frequencies in all directions, and in particular the constants of propagation. The propagation phase velocity is constant, that is, the wave number is directly proportional to the frequency. So today what we're going to start discussing is periodic problems, and see and provide a mathematical justification for the picture I started with in the first lecture. So let me, oh no, I can't write with that. So let me maybe remind you what we had yesterday. So we had the wave equation, which I wrote in this form. What did I write here? XL, right? And we were looking for solutions, plane wave solutions, because the material was homogeneous. So that meant that these constants were independent of x. So you could seek solutions of the following form. Oh, just put J here. And what did we see? We saw that 1, for all omega, there exist solutions star, right? And 2, for every omega and all k hat, where you remember that k hat is the direction of propagation, there exist solutions star. And the third thing we showed was k hat is actually proportional to omega. So today what I want to start discussing now is periodic media. So I will start with a picture. So what we're going to look at is, again, we'll be just considering the whole space. And let's imagine that our media is no longer homogeneous, but actually it's just made up of two different homogeneous material. What's happening? Ah! Thank you. So now the material is periodic, but it's just like, say, a composite material that we've made by hand. We just have two homogeneous material, and one of them is periodically dispersed through the other. And for the moment, I'm not going to talk about what type of geometry the inclusions will have or anything. We'll just use this picture to depict some geometry. And these inclusions are separated. You can put an arbitrary period here, P1 and P2, but of course without loss of generality I'll just say that the period is 1, because whatever the period is, I will just do a rescaling by a change of variables. The equations will not change their form, because the equations are invariant on the change of variables. So I can always set the period to be 1. And this will be the so-called periodic reference cell, Q, where this length is 1, this length is 1, and the Q is split up into two regions just for the sake of discussion. We have one material living in region 1 and another material living in region 2. And I need a little bit more notation. I will call the interface between the two regions gamma, and it will have an outward unit normal, n. So I have two regions now, omega 1 and omega 2, which omega 1 is the region without inclusions and omega 2 is the region with inclusions. And what I want to do is I want to study waves propagating through this material. So, and as we saw yesterday, the equation from applications, the equation of study is always going to be the wave equation of this form. But how does the wave equation look here? Well, first of all, let's denote by our unknown whatever physical phenomena we're trying to study. We'll denote it by U1 in region 1. And we will denote it by U2 in region 2. Okay? So this material should satisfy the wave equation in each region. From exact same arguments as yesterday, the material is homogeneous in this region. So I will denote by 1 here. And I want to write the indices. Now I'll just write it in vector form. If you prefer me to write it the other way, just say. Okay? And this is U1 in region 1. And the exact same for some density and for some material parameters, for some tensor C. And the same thing in region 2. Yes? Now, what happens at the interface? Well, we need some kind of conditions at the interface. And I'm going to introduce some natural conditions, which are these conditions that say there is some kind of perfect contact between the two materials and they don't separate in any way. They are just one continuously changes into the other. And the first condition that said this is we would naturally expect that the solutions are continuous across the interface. But we need to complement this with one other set of conditions. And let's have a little aside to motivate what this other set of conditions are. So let us imagine we have, so we just draw the following picture. So we have region 1 here, and we have region 2 here. Not thinking about periodic, we've just taken two homogeneous materials and we stick them together. Then, from the equations, what do we have? We have region 1, union region, no, I'll write it this way. So, rho 1, and then rho 2, sorry, e squared, right? Well, just using the wave equations. Okay, so we know this is true. And now imagine I just take some kind of box, some line integral like this, and I put myself actually inside this region. So I call this V1 and V2, and I have some, what do I want to call this? Gamma 1, 2. This line, which is a common boundary between V1 and V2. So what I could have written here was V1, V2, this one and this one, right? And now if I do integration by parts here, what is happening? So I won't do all the calculation. It's kind of, so basically I'm going to use integration by parts here. So now I will have dv1 C1 grad U1 dot n. This is divergence theorem, right? The divergence of a field is equal to the flux across the boundary. Okay? And now I'm going to imagine that there is a small, this length is a small parameter delta. And what I'm going to do is I'm going to send delta to 0. And I'm going to assume that my material is behaving in such a way that these quantities here are not becoming arbitrarily large in this region as it contracts to 0. And then as you send delta to 0, maybe as an exercise to convince yourself, what you would end up with is the following. So I have to draw a picture here. Maybe, oh, we only have black. Oh, no. So when I integrate across these contours, these line integrals for V1, you always take this direction, right? For V1. And for V2, I take the other oh, maybe a different color. And for V2, I take the other direction. Like this. So the integral, so this part of the boundary in V1 is minus the integral of this part of the boundary of V2. So when you pass to the limit, you will end up with something like this. Well, exactly this. Right, and now we use the usual, relating to the question yesterday, we're always in the continuum approximation here. So now we just argue by the arbitrariness of the choice of this contour that the additional natural boundary conditions I should impose here is that the flux, not only is the field continuous, but its flux must be continuous across the across these interfaces now. Oh, I called it gamma, right? Well, gamma, this is gamma. What I meant here is probably gamma 1, 2, right? Because I want to, it's a periodic structure that occupies the whole space. There are infinitely many interfaces. So you can see that this is already a lot more complicated than the homogeneous case. You have to solve the homogeneous wave equation in each region, and then you have to satisfy these conditions across infinitely many interfaces where the material changes from one to another. And what I will do is I will rewrite this equation in a compact form. So if I introduce the following tensor, so this is a function of x now. Explicitly write it. Oh, so if I put the variable, I should write it carefully. So I introduce these two objects. Okay. Let's get rid of this little aside. Then the field U solves the following problem: rho of x maybe I write it in component form again. Now it's a function of x with discontinuities across the interface. Okay. So this is, I'm just going to write this symbolically now. I'm not going to any discussion about how you can make this more precise. Well, maybe a small discussion for those of you who know enough about weak formulations in Fourier distributions. This actually holds in the weak sense, so you can make sense of these equations precisely in this form. But if you're unfamiliar with this stuff, I will just continue to use this equation now, but you always have to remind yourself that you have to solve this equation in this region, this equation in this region, and satisfy these infinitely many interface conditions. Okay? So now I want to study some waves, time harmonic waves. Of course, straight away, I can't use an ansatz like this because this ansatz is intimately related to Fourier analysis and the Fourier transform, and the reason it works is because these coefficients are independent of the spatial variable. But these coefficients are not independent. But there is a natural generalization of the Fourier transform to problems with periodic coefficients, and there is a natural version of the plane wave, and this is called the block wave. So let's introduce the block wave. And these are solutions of the following form: ui of x and t. I did it again. I didn't introduce the variables correctly yesterday either. Okay, and now I'm going to have a plane wave solution, plane wave manifold, but I don't want to put a constant amplitude here. the amplitude that you actually put here now, what letter is good? W will work. Now I have to put a function W, and this function W is going to be taken to be periodic. So Q is this set here, and ER is the Euclidean basis vector. Okay, so this function is periodic in each and every direction. So there is a little bit of a natural difference here between the block wave and the plane wave, precisely in the fact that this is now a function and not a constant. So now I'm going to. So here, if you remember everything I was saying yesterday, you can imagine now you have some plane wave that is propagating in a certain direction. But now instead of the amplitude being constant, as the wave propagates, its amplitude will vary in a periodic fashion. And I'm going to plug this equation into our now periodic wave equation. And you will end up with the following problem. Oh, maybe I'll call this 1. Maybe I'll call this 2, sorry. And you will end up with the block problem, which it is, as it's called in literature. Okay, so you plug it in, and what do I end up with here? So I have omega squared. Let me call this variable y. I'm just changing to variable y. I'll explain why in a minute. Just x is the variable in the whole space, and I want y to be the variable on the periodic reference cell. Okay, and w is periodic. So we just write this again. Each component of the vector is periodic. So we arrive at the block problem. Okay, and now it's just the same game as yesterday. We want to understand for what frequencies omega, what wave numbers k do we have such that this solution satisfies this equation. But maybe we just have a little aside for the moment. In the homogeneous material, k was taken to be an arbitrary vector in Rd, right? But if I just have a look at this ansatz here, and imagine that I replaced k with k plus 2 pi. Okay, well, what does this look like? This looks like e to the I k x minus omega t multiplied by a function e to the I 2 pi. 2 pi is kind of strange. What do I mean? Because it's in multi-dimensions. I put ER here. Say in a Euclidean direction ER. Okay? Now if you just look at the form of this equation, we have this quasi-periodic manifold and then a periodic amplitude. But this is also a periodic function. So I could have set this to be W. And it solves the same problem. So what does it mean? The solution is periodic in K as well as in X. So I only have to restrict K to a periodic cell, which is 2 pi times the spatial period. And this is called in literature the Brillouin zone. And commonly people like to, and you just have to pick some interval of a size 2 pi. And usually, people usually pick K to be in this interval. But the period's 1 here, yeah. So, so you would, of course, if the period was A, I would have to put 2 pi over a here for this function to be periodic. That's what Curry was just saying. But I precisely didn't want to remember where a was and all of this stuff because I just wanted to rescale it out in the beginning. The essence doesn't change. So the first change to the homogeneous problem. I just restrict K to be some compact set of this particular compact set. And now I want to ask, just like yesterday, we plugged let's remember, we plugged in the plane wave ansatz, and what we ended up with was an algebraic equation. But it was an eigenvalue problem. But here we have an eigenvalue problem as well. And actually, for this problem, there are infinitely many eigenvalues and infinitely many eigenfunctions, and the eigenvalues go to infinity, and the eigenfunctions form an orthonormal sequence in L2. So, so there exists a sequence, and a sequence of eigenfunctions Oh, it's the same problem. Okay, I'll write it like this. Nobody told me. Of course, I wrote the Gelfand. I didn't write the block problem. When I plug in this ansatz, what happens when I take a derivative with respect to x is it's going to kick out a k. It was missing. Nobody was brave enough to tell me that I made a mistake, I suppose. But it's, well, I'm not going to get into a discussion as to why I made this mistake, but the problem's equivalent, basically, if you change the boundary conditions appropriately. So I've just modified it because, of course, if I take the derivative with respect to x here, first I differentiate this function, but then by chain rule, I then have to differentiate the product rule. Then I differentiate this function, so I get a derivative plus an ik. So this is the problem I'm going to study. So there are infinitely many eigenvalues. They depend on k for a fixed k. Fixed k. And there are infinitely many eigenvalues that depend on k. Infinitely many eigenfunctions that depend on k. K and x. I'll write it like this. To this problem. And the index form is equivalent to this vector form of the problem. And I write I here. Again, this is not an index, this is a labeling. And I here. So we can do the same thing as yesterday then. So maybe I can pick, but of course now, you remember what happened yesterday? Here we just had a matrix. And this matrix was too homogeneous with respect to the parameter k. So after I did a rescaling, the matrix just depended on the direction, and we saw that the frequency was proportional to k. There's no such relationship here. If I replace this by absolute value of k hat, I certainly cannot pull it out of the equation. So these eigenvalues are complicated with respect to k. But anyway, there are infinitely many of them for each fixed k, so I just have to pick my omega now so that it is one of the eigenvalues of this problem. And if I do this, then I have a wave of this form propagating, which solves this equation, a propagating wave. And let me draw the following picture. We will analyze it a little bit more. So I'm rubbish at drawing surfaces, so I'm going to stay in one dimension, or you can just imagine I've taken the absolute value of k, whichever way you prefer. What do we have? So for each k, and I didn't say that these eigenvalues are labeled according to the min-max theorem. So that means they go to infinity basically. And you repeat them according to multiplicity, because they might be non-distinct, these eigenvalues. But let's draw what happens. So if I set k to be 0, then I have an eigenvalue here, maybe an eigenvalue here, and an eigenvalue here. The first eigenvalue, lambda 1, 0, lambda 2, 0, lambda 3, 0. But this problem behaves linearly. Well, it's even analytic with respect to k. But all I care about is that it continuously behaves with respect to k for what I'm going to say. So it means that the eigenvalues continuously behave with respect to k. So if I start sweeping k, then, and in 1D I know quite a lot more. I even know what the shape of these bands are going to look like. All the odd bands are continuously increasing functions of k, and all the even bands are continuously decreasing functions of k in 1D. So you would expect pictures like this. And maybe the third one here is now going off again, continuously increasing function. And this axis was omega, the omega axis. So I have lambda 1 of k here, lambda 2 of k here, and lambda 3 of k, and so on, going to infinity. We'll just take it for granted at the moment that this is the general picture. So how is this different to what we discussed yesterday? Well, the first point which I just reminded you about, the first result of yesterday is for all omega you have a propagating wave. No longer true in general, because look here, imagine that I chose my omega to be living precisely in this region. Then it means for whatever k you give me, I cannot find, for this omega, no matter what k you give me, I cannot find an eigenvalue to this eigenvalue problem. So the wave cannot propagate. And this is the mathematical explanation of the picture that I showed yesterday and the physical phenomena that for some frequencies waves cannot propagate through periodic material. And it all boils down to the structure of these eigenvalues and whether or not gaps exist. And there are a few other things you can observe. Of course, like no longer the bands are no longer proportional. And these give you additional properties of the behavior of the waves. For example, they have non-trivial group velocity and non-constant phase velocity. So the group velocity, if you don't know what it is, imagine you have, because these are linear problems, I can take linear combinations of these solutions. And in fact, I should take linear combinations of these solutions and do a Fourier analysis to study the general problem. And what you can have is, with this linear combination of solutions, each of the waves is propagating with a phase velocity in a certain direction. But the entire group is propagating with a group velocity. And because the bands do weird things like become negative at some point, even though all of the individual waves are going in one direction, what we observe is that the wave is traveling in a different direction. And information like that is just readily available by looking at these band structures. So from the point of view of applications, now one important question, and maybe next week, I haven't decided, maybe I'll discuss about proving in periodic material, say in the case of electromagnetism, the gaps can exist and actually determining the gaps in terms of your geometric structure and your material parameters. But for today, oh, maybe this was the most important picture. Okay. Hopefully you guys kept it. But for today, we'll do just explain, maybe not prove, or it can be an exercise for those who want to prove why gaps should exist. And this will start leading to these words like high contrast that you saw in the title that I didn't explain. But first, let us remember if we take homogeneous. So let's go back to yesterday. And now I'll just take the wave equation in 1D. And I just pick some material parameter. And you remember we showed yesterday that omega over k was exactly equal to the square root of A0. Okay? So I could do the same thing that I did here in the periodic material and just draw omega as a function of k. Please remember, this was omega squared. Of course, it was the eigenvalue lambda, and if I just look here, lambda is omega squared. You're going to come across this all the time, so the fact that I did it now will set you up for it. Mathematicians use omega squared because it's an eigenvalue of a spectral problem, but physicists use omega because it's a frequency and it has a physical interpretation. So when you look at some applied articles, you will see omega over k, not omega squared over k. But from yesterday, we saw this. waves were propagating in all directions, and they were precisely propagating like this. So, what are these called? These lines are called light lines in the physics literature. And it means that when you are precisely on this line, you have a plane wave propagating through your material. This is what we showed yesterday. But now, let's put it in the context of block wave analysis. Well, constant coefficients are certainly periodic coefficients. And in fact, I can choose whatever period I like. So let me choose a period A. Not 1, because I got in trouble 5 minutes ago for 1. So we'll do something else. So let me choose a period A. So now I'm just going to pretend that my constant material is a periodic material. So now I know that my wave number k can be taken inside this the set of period pi over a, minus pi over a to pi over a, because the period's a, not 1. So this means actually now I just interpreted this line as being periodic. So what I do is I wrap it around. So when I'm here now, this becomes this point here, and continues on, right? Maybe different color. So this green line now continues here, and this, because I'm using the fact that it's periodic, right? And I only need to consider it in its periodic cell. This line goes here, and again, so on and so forth. Green line carries on over here now. It's these. I am absolutely awful with drawing. Of course, these things should match up. So let me wish I had a ruler. I don't have a ruler. There we go. And so on and so forth. You see, you get the picture, right? Every time my green line hits here, I take it over here and go on. Every time the blue line hits here, I take it here and continue on. So what's important is so now I have found the eigenvalues for the block problem for periodic coefficients in terms of the block parameter. Oh, I should say as well sometimes that now this k is called quasi-momenta in the nomenclature for periodic problems. And I found, and from what we did yesterday, we have found the band structure. And you see, there are no gaps. But that's exactly what we showed yesterday. For all frequencies, waves propagate. So this is the decisive difference between homogeneous and periodic material. So now how can I create gaps? Well, actually, in one dimension, there are always gaps. And let me give you an intuitive idea for this. It can be an exercise. Well, maybe I'll formulate an exercise in a minute. So let me take this equation, A0. And now let me suppose let's consider A equals A0 in the region 0, 1/2, right? And let me consider it to be A0 plus delta, where delta is a small number, in the region 1/2 and 1. Okay, maybe we can, instead of me just talking all the time, you can, and I don't want to go into showing this, but those of you who are capable of doing this, and then we'll so lambda delta, which is omega squared delta, and u delta, solve the problem. Solve 1. So d squared u delta, oh, sorry, we've already done this, lambda delta, so it solves this eigenvalue problem, right? What am I going to write here? Div A delta grad U delta. And I want to do it in the neighborhood of this point. Minus. I blame you. It's all your fault. You did it first. Okay. Minus, of course, in all of these equations. So what I want to do now is I have perturbed my coefficient by a small amount, and I'm going to argue that no matter how small this amount is, it's going to create a gap. And why does it create a gap, and where can it create a gap? Well, the only places I expect it to create a gap are here. So I'm going to be looking in this neighborhood of this point. So what I'm going to argue is, well, for this problem and this point, what is lambda? What is the eigenvalue here? Well, we have a formula, right? So lambda 0 is omega squared. And omega squared is a naught k. So it's a naught pi squared over a squared. And this eigenvalue is simple. We created a degeneracy in the problem by taking the homogeneous problem to a periodic problem and wrapping around our bands. We accidentally created a degeneracy. So this eigenvalue has multiplicity 2 now. One eigenvalue from this band and one eigenvalue from this band. Or to say it in less vague terms, if I just look at the block problem, you will realize that precisely when you consider pi over a periodic functions, which are actually pi over a quasi-periodic functions, block, where k is pi over a, but these are actually 2a periodic functions. So if I try to solve this eigenvalue problem for 2a periodic functions, you will realize that the first eigenvalue has multiplicity 2, and it has 2 eigenfunctions. Well, what is going to be the first eigenfunction of a 2 pi periodic thing in 1D? It can only possibly be sine and cos, and these are orthogonal. But these are the 2 eigenfunctions, right? And now I want to apply regular perturbation theory. So let me introduce a problem, a function u0, which is going to be alpha u plus beta v. Alpha, beta, 2 numbers. Because let's just say we're solving this problem now, where u delta. I should have applied boundary conditions. We should say that u delta of y plus 1 equal u delta of y plus 2a equals u delta of y. So this is the problem. So what I've done is, because I know that I'm at pi over a in block, I substitute pi over a in here, and it precisely just means my function is 2a periodic. And the reason I'm doing this is because I just want to put real numbers here instead of complex. It doesn't really matter. It just makes you, when you do the calculations, you'll be happy for this. So I introduce this function. Oh, it fell on the floor, didn't it? And now we're just going to apply some regular perturbation theory. This is, remember, this is an exercise. So we're going to say, with no justification whatsoever, even though you can justify, let's say that our eigenvalue lambda delta due to a small perturbation delta must be close to the eigenvalue at this point. So, and it's going to be some small change of this eigenvalue. Plus, you can keep going, Taylor series. Remember, I said that the eigenfunctions were continuous. They're actually analytic, so you can do a Taylor expansion. But this is, they have to be analytic in delta. Let's not worry about making it rigorous. We can just continue like this. So now we want to say that our eigenfunction u delta is maybe going to be u0 plus some small change. And what shall I call this? Equation 3, right? And then I'm going to, and then sub 4 into 3 and start gathering terms. And what you will realize for you to do, you will get some matrix M alpha beta equals lambda 1 alpha beta. And M is 2 by 2. And actually, because of this problem and the nature of the perturbation, it's going to be symmetric, this M. Now, what you need to do is you need to show that there are two, that there, say mu1, the eigenvalues of M are distinct, right? They're distinct and they have different sign. So this can be your exercise for those of you who feel like you would like to do this. And what does it mean? Well, if I remember now that mu1 is actually just lambda 1. Just pick alpha and beta to be one of the eigenfunctions when I construct u0. then mu1 will become, well, then lambda1 will become one of the eigenvalues. And then up to a smaller order term, this eigenvalue at this point has done the following thing. The second band has gone up because these eigenvalues have different sign, and the other band has gone down. And what happens here is precisely something like this happens. And because it's periodic, the same thing is we've done the same thing here. And what you've created is, for an arbitrarily small perturbation in one dimension, you've created a gap. So now you've created a spectral gap. So you can see here from this argument that periodic problems indeed do have gaps. Now, in multi-dimension, of course, the arguments will follow through, but in systems or in multi-dimension, you have problems where the picture is far more complicated. There are many more eigenvalues, so even if you perturb some of the bands a little bit, maybe the other bands haven't perturbed enough, so the gap doesn't open. So what you have to do is really, really crank up this contrast, for example. So now you would consider a periodic problem where the ratio of material parameters is large, not small. And this is precisely what we call high contrast problems. And I will get into that tomorrow. But what I would like to do for the rest of what we have today, I don't know how much time I have. Sorry? Tomorrow. Well, tomorrow up to the equivalence class of me working. So, ignoring the weekend. So, Monday. So what? Oh, I have a little bit of time, right? What time do we finish? Sorry? Does anybody know? In 10 minutes. Oh, okay. Maybe I won't have time. Or, well, I can certainly fit it in 10 minutes, but maybe nobody will understand anything. So, but let's just jump from these. So what I've done now is discuss periodic problems, motivated why we would want to study periodic problems from the point of view that they have this surprising but very nice feature that you can actually localize waves. You can trap them. I mean, if you wanted to confine a wave in some region, you would just put a periodic structure around this region, and if the wave's frequency lives in this zone, then it will not propagate into the periodic structure. And on Monday, I will discuss there are even more interesting effects in periodic material. Maybe not only frequency, because like I said, in multi-dimension, you would not maybe have this picture of one band, but maybe the first eigenvalue has higher multiplicity. So maybe the second band would do something like this. And then this would become the third band. And then what you had here is not only, I'll draw it a little bit differently. So maybe the second band will have some strange structure like this, but going higher at this end. And you have things like waves propagate, for a given frequency, waves will propagate for some wave numbers, but not all wave numbers. And this sort of feature we would like to exploit in applications as well. But before we understand how we want to exploit them in applications, let's ask the following question. So apparently, periodic media have this ability to stop light from propagating through them. But homogeneous media don't have this property. But we always make some assumption on some level. If we have some microstructured material that's periodic, you will see often, so now that the periodic media can be treated as a homogeneous media. So I would replace the periodic wave equation with the homogeneous wave equation. But if waves behave differently in periodic media to those in homogeneous media, how can I justify such a treatment? So this is another asymptotic analysis regime that Kyria was discussing this morning. So now let's imagine that I take my periodic material, and now this is a composite. So say maybe artificial, man-made, or we're just going to decide that we're not going to say the material is homogeneous, but we're going to say that the material has some periodic structure, but this periodic structure is very, very small compared to the observable scale. So when we look at it, it just looks homogeneous. And this is represented by the fact that we are assuming that the period is very small. Okay? And then I want to say, well, I'm going to send in a plane wave, now. And I want to understand the behavior of this wave with respect to the parameter epsilon. Right? So, well, I'm just going to take, so what do I have here? So, let's set rho to be 1. Rho is something I'm not so interested in, and let's set our periodic coefficients to be of the following form. So they are 1 periodic functions, where C was as before. C1 for y in Q1, and C2 for y in Q2, right? So, I already know what to do now. I have block waves, so I'm going to study the block problem. But first, I formulated the block problem with period 1, right? And I said we can just rescale. So let u epsilon solve the wave equation. So that's d squared u dt squared epsilon equals divergence c epsilon of x here, x and t, grad u of x and t, sorry for the mess, for x in the whole space, right? So first I will just introduce another function, v epsilon of x, and this is just going to be rescaling. Now, I can never rescale on the fly. Why? I don't know why. X over epsilon, right? So I'm going to introduce this function, and now you will see that v will solve... sorry. Only have to rescale the spatial variable, and v will solve epsilon minus 2 now, c of x, grad v, xt. Okay? From a simple rescaling, now I have a problem with period 1. So now I'm going to look at block waves. So, I'm going to say for some k, b epsilon xt looks like e to the minus okay, and we remember that W now solves the block problem. What do we have? We have omega squared equals grad plus ik dot, not div. I was using div, right? Epsilon minus 2 c grad plus ik w epsilon for y in q, right? Oh, I'm missing something on the left hand side. The all important function. Oh, look at this, w and omega. What awfulness. A w epsilon. So it solves this problem, and it depends on epsilon, right? But actually the dependence on epsilon is quite trivial. So I'm just going to take this dependence on epsilon, I'm just going to stick it over here. Epsilon plus 2 now. So we have the block problem, and we have the block problem for a one periodic media that's independent of epsilon. So that's to say, actually, the eigenvalues of this problem are nothing more than the inverse square of the eigenvalues I introduced a moment ago when I was studying the eigenvalues and eigenfunctions of this PDE, or the operator associated to this PDE. So I can draw lambda epsilon. Again, we're going to live in this regime where I don't want to draw surfaces, but you have to imagine that these are surfaces. And what's happening is the first lambda epsilon is actually just epsilon minus 2 lambda 1. Okay, the lambda 1 I introduced before. So this is an order epsilon minus 2. And then the second one, maybe gaps, maybe not. But whatever it is, it's of order epsilon minus 2. And then I ask, well, I have a fixed frequency. Can I see whether can waves propagate or not? And imagine my frequency is fixed. It's not scaling with epsilon. And what you can see is a formal justification at this level, we can go a little bit further at the moment, that says, well, if I have a very small structure for a fixed frequency, if the structure is small enough, then certainly the wave is going to propagate. Because whatever gap, wherever it is, it's scaled 1 over the period squared. So for a small enough microstructure with a fixed omega, this gap is going off to infinity. So the wave will propagate. Now the question is, does it propagate as if it's propagating through a homogeneous material? Still not obvious at this second, because if you're living here, then remember this is omega squared, sorry. In homogeneous material, omega squared is quadratic in k, but it's certainly not quadratic in k. But I keep drawing quadratic near the origin. And there's a good reason for that, and that's because in all of these problems, the eigenvalue of lambda 1 of k is quadratic near the origin. So I combine, so maybe I draw a picture before writing some more words. Sorry? Oh, it's an elliptic problem. Wait. The reason I stand in front of you as a mathematician and not an artist is precisely for this fact. You have to take it for granted that I wanted to draw a quadratic function. Right? And what I've put here in mathematical terms, I will now try, and I said in physical terms, I will try and draw a picture for the physics. So imagine we have a period epsilon. And now we have a wave of fixed frequency omega propagating through this material. Now the wavelength is inversely proportional to omega in homogeneous material. We saw that yesterday. Remember, the wavelength was 2 pi over k, and in homogeneous isotropic material, k, well, in all of these material, k was proportional to omega, homogeneous material. So for a small omega, fixed omega, the wavelength is of a certain size, and you can imagine that, this is a rubbish picture, you can imagine that what's happening is as epsilon gets smaller and smaller and smaller, the microstructure is small with respect to the wavelength. So, and this is the argument you will hear from more applied people. They say that homogenization is nothing more than a long wavelength approximation. What it means is your wavelength is sufficiently long, so when it's passing through a microstructure material, it just sees a homogeneous material. So how can we make some mathematics out of this? Well, I will now not draw, but write something that's to answer Kyriel's question. How do I know that it's quadratic? Well, we can, and it's not. Scalar equations. Even in systems you can do this too, but it's getting a bit more of a pain in the... Let's just imagine now we're just studying a scalar problem. So you can show straight away, first eigenvalue, little bits of work, not too much work. Regular perturbation theory, as in the exercise I showed you, that the first eigenvalue is quadratic plus order k squared near the origin. Well, actually, this is just true for the whole block band. You can prove an error-bound constant k squared. If it's order k squared near the origin, of course, it's going to be away. So, well, the error estimates, I mean. And the second thing is, let's take the first eigenfunction corresponding to the first eigenvalue. So we're in the case of scalar equations, and the first eigenvalue is simple. And what you will find is the first eigenfunction utter an appropriate whatever normalization, that this is true, right? Now, what does this mean for our u epsilon problem? So what we have is we have u epsilon of x is what was it? Was it did I do the scaling wrong? I feel like I did the scaling wrong here now. Yeah, I think I told you that I would get this wrong. Nobody picked me up on it. Of course, it has to be like this. So now v is x over epsilon, and I said that v was a block wave. Right, and I'm going to take it to be the first, for the first block wave. So I'm in the first band. So this is square root of lambda 1 of k, and this is omega 1 of k of y. Yeah. Here, yeah, x over. What do I want to put? X over epsilon, right? And then this is e to the minus k over epsilon x minus. I shouldn't have studied this. What should I have done? Okay, I didn't want to. I wanted to ignore the time dependence bit for the moment. Right. So what do we have here? Well, I didn't want to do it like this. Sorry. Just let me take my notes, or maybe I'm running out of time. Okay, I want to keep omega here, just for the moment. Yeah, okay, I keep this. So what does this look like? Well, this looks like a plane wave. No, not a periodic, not a Bloch wave. Traveling through the frequency, through the material with a frequency omega given by the square root of lambda 1. So what is it saying? We have lambda 1 of k is actually a2. Lambda 1 of k is actually a2 of k. Oh, there was an epsilon here, right? Because there was a there was a scaling. Omega epsilon was supposed to be what? Epsilon inverse of lambda 1. Or was it epsilon squared? Epsilon squared of lambda 1. So epsilon squared of lambda 1 is omega 2k plus order k cubed, right? But let me take the k over to the other side. Go write this on the next line if you like. So I put a epsilon minus 2 here. But I'm going to do two things. I'm going to add an epsilon to this. So epsilon minus 2 is epsilon times epsilon minus 3. So I'll put an epsilon here and put a k over epsilon here. Okay? And what is happening? Omega 1, well, this is proportional to 1 plus OK. Right? But I'm going to play the same trick. I'm going to put an epsilon here and divide through by an epsilon here. So now what does it look like? Well, it looks like that our eigenvalue is approximately, up to leading order, the solution of the problem. So now I set, sorry, let's pick a vector tau, set it to be k over epsilon, basically, fixed tau. So it looks like I have up to order epsilon for fixed tau, I have omega squared equals a2 tau dot tau. Okay? And the eigenvalue omega is of the, what function do I want to look at here? And omega 1, which is approximately some function alpha, approximately of the form e to the I kx minus omega t times a constant 1 up to leading order, again order epsilon plus order epsilon plus order epsilon. That's what we have written here, just in another more precise form. And of course, what does this mean? From the yesterday's analysis, this is a plane wave and it's propagating from a material that satisfies this equation up to leading order. So actually the function 1, so I call this omega naught, say, omega naught solves the problem. No, I call this omega naught. Omega naught solves the problem. D omega naught squared by dt squared equals div a2 grad omega naught. Up to order epsilon. So what does it mean? So for a fixed frequency and a small enough epsilon, then our wave behaves approximately like a plane wave, and the material it sees is a homogeneous material, and its material parameters are precisely given by this constant A2, which is the Hessian of the first band function at the origin. And I don't probably have no more time, right? No? Sorry? No more time. So maybe I will now write a theorem next week that puts this in a more rigorous setting. But, well, I can make a claim that I can test, that I can prove if anyone wants to test me. But everything I've said today is pretty much enough to prove the homogenization theorem up to order epsilon in terms of waves for an equilibrium problem, for a stationary problem. Okay, thank you for your time. Oh, any questions? Of course. I said, in general, yeah, I know, maybe it's a bad choice of words. I know I proved that this is not true myself with Ilya and Valery, but what I meant to say is up until this work of me, Ilya and Valery, people thought you need high contrast to open gaps. So it is, high contrast is sufficient to open gaps, right? But not necessary. I was just trying to motivate high contrast problems. Look, from a mathematical point of view, you want to introduce a high contrast in your coefficients. You're talking about a physical point of view of high contrast. What I wanted to say is, if I put some high contrast into my equations, just from a mathematical perspective, then you will open gaps. Now, how you introduce high contrast into your equations does not necessarily mean that you have to introduce high contrast into your materials. But you can... So high contrast in the equations can arrive due to some other physical effect. But it still manifests as high contrast in the equations. I didn't. Of course, that's for Monday. I didn't talk about high contrast today. This is all moderate contrast. So you ask me on Monday if you still have it. Today was moderate contrast. Any other questions? No? Okay, well, so on Monday, we will talk about... So this result pretty much tells us that if I construct a microstructured material, then I'm not going to expect that this material will have the nice properties that periodic media suggest it should have. Because for a fixed frequency, due to the microstructure, all of these wonderful properties have gone away to infinity. And I just end up with something that's approximately homogeneous. So the mathematical question is now, what can I do to stop these bands going off to infinity? So that if I create a microstructured material, can I open gaps for a low frequency, which in applications is precisely what we want to do. Here we can have gaps for high frequency, but in applications we want low frequency. So we will explore this on Monday. Thank you for your time.